All right, so we've arrived at chapter 10, which is pretty exciting. Chapter 10 is hypothesis testing for one parameter. And it's exciting because this is really what we've been building up to. I know I said that in chapter 9, that a lot of what we've been doing built up to that, but chapter 10 really kicks it into high gear. In 10.1, we go over the language of hypothesis testing. Oops, can't spell. Nothing's different. Even at home, I have a tough time spelling. So 10.1 is about the language of hypothesis testing, a lot of vocabulary and why we're doing what we're doing in this chapter. And then 10.2 and 10.3 are hypothesis testing for proportions and hypothesis testing for means. Just like in chapter 9, we learned how to construct confidence intervals for those two things. But really in 10.1, what this video is all going to be about is why we're doing what we're doing and the vocabulary that comes with it. Very, very little math is going to come up in this video. Like I said, this is more like the theory section. All right, so the language hypothesis testing. And the way I'll start this is I'll start this with an example. And the book comes up with a really, really good example to really kind of lead us into this section. And let me propose a scenario. You and your friend play a game. Where you flip a coin. If it lands heads, you win, let's say, $10. You lose $10 if you flip tails. So you and your friend are gambling. You flip heads, you win $10 from your friend. If you flip tails, you lose $10 to your friend. Oops. Give me 1 second here. I don't know what I did. Oops. All right, so you're playing this game, and now here's the scenario. You flip the coin, and it's tails. So you end up losing. All right, you're going to be sad for a second. Then you say, okay, let's play again. You flip again, and it's tails. All right, so now you're out $20, and you're starting to get a little frustrated. You say, let's go again. Third flip, also tails. Let's say you play again and again and again and again. In fact, after playing, let's say 6 times, the coin landed tails. All 6 times. And my question to you would be, do you expect your friend is cheating? You know, you play 6 times back to back to back to back to back, and it keeps coming up tails. You keep losing money. The question is, when do you expect your friend cheating? And the tails are more likely to come up than heads. You know, maybe they're using a weighted coin or something. And let's not stop this at 6 times. When do you start to expect, okay, something's fishy here. Something's not right. This isn't normal for this coin to come up tails this many times in a row, or this percentage of the time. When do you start to worry? maybe I should put friend in quotes because if they are cheating, maybe they're not really your friend. But this is really what would get us into hypothesis testing and statistics is when do we start to say, okay, these results are kind of going against what I would expect. So maybe what I expect is wrong. You know, I go into this game expecting that the coin is fair. After it comes up 6 times tails in a row, I'm going to start being like, okay, let me see this coin. I don't trust you. All right, so let's get back to statistics and not this friend who's taking all your money. For hypothesis testing, we're actually going to start involving 2 hypotheses at the same time. And before I start differentiating between the 2 hypotheses, let me make sure everyone knows what a hypothesis is. Which I'm assuming a lot of people have heard this word before, or if you've taken any science class within the past, 300 years. A hypothesis is a proposition assumed as a premise in an argument. And a lot of people hear the word hypothesis when they're doing like science experiments. You hypothesize what do you expect to happen, you conduct the experiment, and at the end you usually make a conclusion about your hypothesis. You either achieved what you thought was going to happen or you didn't, and here's the evidence to suggest otherwise. And it's the same in statistics. So for statistics, let's be specific here. For our course or our class, a hypothesis is a statement regarding a characteristic of one or more populations. In other words, it is a statement regarding the value. Oops, let me erase that. That doesn't look good. The value of a parameter. Right? Parameters are values about a population, so it makes sense. So hypothesis in general in life is a proposition assumed as a premise in an argument. Great, but that's pretty generic. In our class, a hypothesis is a statement regarding a characteristic of one or more populations. Specifically, it's a statement regarding the value of a parameter. Hypothesis testing is a mathematical procedure. We can just say a procedure based on sample evidence and probability. We're never going to get away from that word, are we? Probability. Used to test statements regarding a characteristic of one or more populations. All right, so I just want to recap real quick because it is important that you guys understand why we're going to be doing what we're doing, because like I said, the problems are a little bit, I don't want to say intense, but they're definitely a little bit more involved than what we're used to. So we are going to have a hypothesis, a statement about the value of a parameter, something like, something I've been claiming all semester is that the proportion of people who are left-handed is 13%. You know, I've been using that, and no one's kind of called me out on it. Where did that number come from? Where's your evidence? Everyone's kind of been assuming it's true, but let's say that's the hypothesis, that it's 13% of people are left-handed. Well, then what we could do is we can go test that hypothesis through hypothesis testing. We do this procedure mathematically. We draw samples, right? Sample evidence. Let me highlight that. Sample evidence. Why do we need sample evidence? Because the hypothesis is based on the value of a parameter. And like we've been saying all semester, we can't actually go out and find the value of the parameters, right? We go out there, we get sample evidence. So if my hypothesis was that 13% of people are left-handed, and you go out there and gather sample evidence showing, let's say you sampled 1 million people, I'm sure you can't, but let's say you do, and you find it's actually 30% of people are left-handed, wouldn't you come up to me and say, actually, I think it's 30%, Nick. I don't think it's 13%. Look, I sampled 1 million people. Here's my evidence. And that's what hypothesis testing will do. Hypothesis testing will get a sample together, produce a result from that sample, a statistic, and that statistic may be evidence enough to refute the original hypothesis. And in this case, that the proportion of people that are left-handed is only 13%, and you go out there and you find, oh, well, actually, it might be closer to 30. So that's the whole point of this this chapter. Keeping that in mind, let's give some bare bones steps of a hypothesis test. This is bare bones. This is not a particular example, but the steps of hypothesis testing, the first thing we're going to do is make a statement about the value of a parameter. Something like I just said. I say that the proportion of people all over the world that are left-handed is 13%. Oops, I don't know how to number. Number 2 would be next. 2. So after that statement's made, you would collect evidence. In other words, sample data. Right? There's no way to actually go out and talk to every single person in the world. Are you right-handed or left-handed? To test the statement. Oops. Let me erase the period here. To test the statement. So you go out there, you collect your evidence, and then you analyze the data. And assess the plausibility of the statement. I mean, that makes sense, right? What we're going to do is somebody makes a statement about the value of a parameter, like I say 13% of people are left-handed. Then you go out there, you collect the evidence, you go out and sample 1 million people, and then you analyze the data and assess the probability or the plausibility of the statement. You find it was actually 30% of people are left-handed in that big sample you took, so you would think my statement of 13% is probably not accurate. That's just the overall general steps. There's a lot of math involved, which we will get to. We will have 2 hypotheses in every hypothesis test. And the two hypotheses, the first one is the null hypothesis. Which is denoted HO. That's the way I always see it. It's read H naught. You might hear me say HO. Just depends on how I'm reading it, I guess. I don't know. Denoted HO. It's H with a little subscript of a 0. H naught, however you want to call it. This is a statement, or the statement, to be tested. This is often called, at least I call it, the claim. Oops, forgot the word the. Oh, sorry about that. I missed all the erasing. So you might hear me call it the claim. So the null hypothesis, denoted HO, is the statement to be tested, often called the claim. This will also always, for all our purposes, always involve an equality. And in math, an equality just means that it involves an equal sign. So we have two hypotheses in every hypothesis test. The first is the null, it's the claim. I claim that the proportion of people who are left-handed is 13%. And the other hypothesis that we will involve is the alternate hypothesis. This is denoted with an HA or H1. I'm partial, I guess, because this is the way I learned it. I learned hypothesis testing with an HA and an HO. The book, for some reason, uses the H1 notation, I think. Give me a second. Yeah, they call it H1. So either one is fine. I like HA because, I don't know, stands for alternate. This is a statement we will test the null hypothesis against. It may be what evidence supports. The alternate will also always involve an inequality. So the null hypothesis always involves an equality, and the alternate will involve an inequality, which in math could be less than, greater than, or not equal to. Those are the three inequalities we'll talk about. So the null hypothesis is the claim. For instance, I claim 13% of people are left-handed. The alternate, denoted HA, would be what we test against. It may be what evidence looks like it's supporting. So if you went out there and did sample 1 million people and found that it was actually closer to 30% are left-handed, you would probably think, hey, it might be greater than what you were claiming, Nick. So let's do a quick example. of setting these up, because setting up HO and HA, or H1 if you prefer that notation, setting up HO and HA will always be the first step in any hypothesis test. All right, so let's do a quick example. Of setting up HO and HA. And let's see, what did they do? All right. Let's say I claim that 42% of all of my statistics students earn a B in my class. You randomly sample let's say 106 of my former students, and find that let's say 39 earned a B. Conduct a hypothesis test. We can't really do that yet, but to determine if the proportion of students that earn a B is actually less than what I claim. Okay, so in this example, we're really going to stop after what is the first step of hypothesis testing. I haven't really gotten into the math yet. I just want to set up HO and HA. That's really all I want to do, setting up HO and HA. I haven't really done anything else, but I want to be able to make sure that you guys know how to set up HO and HA, the two hypotheses. So HO and HA. And we use colons because HO and HA are statements, right? So HO. What is the statement that I am making that we will use as the null hypothesis? Now I'm going to scroll back up. That null hypothesis denoted HO. This is the statement to be tested. This is often called the claim. And this will also always involve an equality. So what did I claim in this? Well, I claimed that 42% of my students earn a B. So, in other words, my null hypothesis is that the proportion of B's is 42%, right? That is what I claimed. And the alternate, what is the alternate? What is the definition of that? The alternate hypothesis, denoted HA. This is a statement we will test the hypothesis against. It may be what the evidence supports, and it will involve an inequality, meaning less than, greater than, or not equal to. So what are we going to test against? This said, conduct a hypothesis test to determine if the proportion of students that earn a B is actually less than. So my alternate would be the proportion of B's is less than what? Less than what? Well, less than what I claimed. Less than 42%. That's what the alternate is. And the alternate, it's worth noting, note, the alternate should be the same as the null, except instead of an equality, we should have an inequality. The two statements should be the exact same statement, except for this part right here, which makes sense. The null hypothesis is the claim. I claimed 42%. And the alternate, you're thinking, oh, well, it might be actually less than 42%. And in some problems, you're going to think greater than, and some you're going to just say not equal to. So keep in mind, it will always be given in the problem somewhere. Like this says less than, greater than would say greater than. Not equal to could be, oh, is it different or has it changed? You know, it doesn't give you an indication of less than or greater than. And of course, less than and greater than can be hidden in the normal ways I've been hiding them before. Like for instance, greater than I can phrase as at least, right? You need to be at least 21 or older to enter this bar. That means 21 and up, right? It means greater than. So just keep an eye out in the problem themselves. It will have the inequality kind of indicated in the words. Yeah. So it's worth noting this part right here. That's a lot of writing for math. And so what we normally do is we just shorthand it. So really what I would write, the proportion of B's is 42%. I wouldn't write all that out. I know what the situation is. The situation is proportion of people who earn a B in my class. I would just write that the true proportion is equal to 42%, right? That's how we write that in math. The proportion of B's is equal to 42%. Same thing with the alternate. The alternate, I wouldn't write this whole thing out. The proportion of B's is less than 42%. We can write that in math as the proportion is less than 42%. This is how I will write my hypotheses, and this is how you should too. So write hypotheses like this. Just to recap, HO should have an equal sign and the claim. HA should have less than, greater than, or not equal to in comparison to the claim. Also, it's worth remembering, I don't know how many people will do, remember we will be studying hypothesis testing for proportions, which we denote, which is the letter P for the parameter, and means, which we denote with that mu, that Greek letter, that fun one. So that's why I used P up here, because the question was about proportions. It was about percentages, right? So in my hypotheses, I used P. The claim proportion is that it's equal to 42%. That's what I claimed. And the alternate is that the true proportion is less than 42%. we will do hypothesis testing for means. I can claim that the average salary at this company is $50,000, and you say, oh, well, maybe it's less than that or greater than that, I don't know. But if I was talking about averages, these p's, instead of writing p's, you'll use mu, because you're talking about averages, you're talking about means instead of proportions, which are p's. So make sure this symbol is right too. So HO and HA, HO will have an equal sign about the claim, HA an inequality in the claim, and then make sure you're using either p or mu depending on whether we're hypothesis testing proportions or means. All right, so that's setting up the beginning, setting up the two hypotheses, a claim and an alternate. And then after you do that, let's scroll back up. So there was a statement made about the value of a parameter. Like in my example, I just claimed that 42% of people in my class get a B. Then we collect evidence to test the statement. Some math goes on here, and then analyze the data and assess the plausibility of the statement. So we're going to be skipping this middle part of actually doing the math to test. I'm going to jump straight down to the possible conclusions we can make. And then the next two sections, 10.2 and 10.3, will go over that middle step. How do we actually do it mathematically? So let's jump to the conclusions. So possible conclusions made after a hypothesis test. First possible conclusion, we reject the null hypothesis. That's the first possible conclusion that we can make. Yep. Sorry, I lost my place in the book here. I'm going to go off book. That's fine. So the first possible conclusion we can make is we reject HO. This means there is sufficient evidence against HO and in support of HA, the alternate. So the first possible conclusion we can make is we reject the null. So for my example about the people who get a B in my class, I say it's 42%. You go out there, you collect evidence, and you, at the end of your hypothesis test, say, actually, I reject your claim, Nick. I don't believe that the percentage of people who get a B in your class is 42%. I reject that idea. Evidence supports this alternate, that it's actually less than that, something like that. You reject the claim. The second possible conclusion we can make is, and a lot of people would say, we accept HO would be the other possible conclusion, but it's not that. We fail to reject HO is the other possible conclusion we can make. So we can reject HO or we can fail to reject HO. There's no other things. I don't want you to ever say you accept HO. Do not say that. So we fail to reject HO. This means there is not enough evidence against the claim to suggest it is false. It's actually kind of like how our legal system is set up right now, right? When you go to court for a crime, you're either found guilty or not guilty. It's not you're found guilty or innocent. Same thing in statistics. We either are rejecting the null or we are failing to reject the null. We never want to say we're accepting it. And here's the reason why. All right, so if I claim 42% of my students get Bs, something that would make you reject HO, let's say you go out and you sample a bunch of my previous students and you find only 10% ended up with a B. and I'm claiming it's 42%. That's going to probably end up with rejecting my claim. You know, I'm claiming it's 42%, and you get enough evidence to suggest it's as low as 10, you'd be like, no, I reject your claim, Nick. Something that ends up in failing to reject is, let's say I claim that 42% of my students get Bs, and then you go out there, you sample a lot of my previous students, and you find that it's 41% said they have Bs in my class. Well, that's not a lot of evidence to suggest I was lying, right? If I say 42% of my students get Bs, and you go out there and you find it's 41%, you are pretty close to what I said, right? You might have just gotten a few more, a few less people who had Bs, because there's no way you talk to all of my previous students, right? So you're going to get something from your sample that's not going to be exactly what I'm claiming, even if what I'm claiming is true. So you don't have enough evidence to suggest that I'm lying. You have some evidence that it could be slightly less, but not enough to say, no, Nick, you're wrong. And so that's the difference. Sometimes evidence will be overwhelming enough that you're going to say, no, you're lying, Nick, that's not what it is, because the evidence is so sufficient against it. But other times, you're not going to have enough evidence against me to say that claim's not true. I can't disprove it. What's interesting is you'll never be able to prove me right, though. Unless you are able to go out and get the actual parameter. The only way you would prove me right is you talk to every single student I've ever had. And that's just not feasible. That's the whole point of statistics, right? So these are the two conclusions you can make. You either outright say, nope, I'm rejecting the null hypothesis, or you can't reject the null hypothesis. And with this comes some mistakes we can make. So what are the possible outcomes? So there's 4 possible outcomes that can be made. Let's say the first possible outcome, you reject HO and in reality, HO is false. This is good. If you reject HO and in reality HO is false, you rejected the idea of HO, which is good because it's false. So I claim 42% of my students get Bs, and you end up rejecting it, and you say, oh, no, evidence suggests it's only 10%, Nick, or something like that. And if I was really lying about what percent of my students get Bs, then you did the right thing. You rejected my claim, because in reality it was false. The second possible thing that could happen, you reject HO, and in reality, HO is true. So I say that 42% of my students get Bs. You go out there, you do some math, you sample, and you say, no, I don't believe you. I'm rejecting that claim, Nick. When actually I have the grade books to prove it. I have all of my previous students. I say, look, it's 42%. You just happened to sample a bunch of people that failed my class or something. Your sample was bad, something else. But you end up rejecting my claim, but it was true. I didn't lie. But you ended up, through the math, making the wrong conclusion. This would be bad to do. This can happen, though, in real life, right? I claimed something, you say it's wrong, and it actually was right. This is called, there's a special phrase for this. This is called a type 1 error. Another possible outcome, you fail to reject HO, and in reality, HO is true. So, keep going on with the same example. I claim 42% of my students get a B. You go out there, you find it's 41%. You don't have enough evidence against my 42% claim. You know, you only had 41% as your evidence. You don't have enough evidence against me. You end up not rejecting it. But in reality, that's good that you didn't reject me or my claim, because in reality, that claim I made was true. That's good. You don't want to reject a true claim. But at the same time, the fourth possible outcome would be you fail to reject HO. So you did not reject the claim, and in reality, HO is false. This is called a type 2 error. So this would be the last possible thing that could happen. You end up not rejecting my claim, but it was false to begin with. That's not good either. So I claim it's 42% of people get a B in my class. You go out there, you find it's 41%. So you don't think that's enough evidence against me and my claim. So you say, okay, I'm not rejecting that it's 42%. I'm okay with that. I'm not going to reject that. But what if I lied and I just boosted it, by 1%, that it is actually 41% get a B in my class, and I rounded it up to 42 because that makes me sound a little bit better of a teacher. So I did lie, but your evidence didn't refute it, in which case you made a type 2 error because you were supposed to refute a false claim, but you didn't. You failed to reject it. So there are two types of errors you can make by making the wrong conclusion. You can either reject HO, but it was actually true. So you said I'm lying and I'm actually not. Or you did not reject my claim and I was lying. Those are the two possible things that could be wrong, but hopefully we fall into one of these two categories, number 1 or 3, that you either rejected a false hypothesis, that's good, or you failed to reject a false null or you failed to reject a true null hypothesis. Ugh, tripping over my words a bit. So since we don't usually know if the claim is true or not, something like my grade book and what percent of my students get B's, we can go through the history, I guess, and figure it out, right? Whether it's true or not. I could figure out the parameter. But if I made a claim that's a little harder to check, like I claim that 14% of people smoke, you're never going to know what the true reality is. You might actually fall into one of the two error categories. And so this is a little bit higher level math than what we'll get into, but for all hypothesis testing problems, we will set the probability of making a type 1 error at the start of the problem to be alpha, but you've seen the symbol before. This is also called the significance level. Of the hypothesis test. You've seen this before, this alpha. You've heard this phrase before, significance level, when we did confidence intervals. to make things easier on you guys in our class, we will use a significance level of alpha is equal to 0.05 for all problems. So this significance level alpha, basically it's set at the start of the problem in real life to limit this possibility here, that you end up rejecting a hypothesis that is actually true. So you end up saying, no, Nick, I don't believe 42% of students get B's in your class, but that actually is the case. So you end up refuting the claim when it's actually true. So this is usually set, the probability of making this error is set at the start of the problem, and we're going to make it 0.05 to make things pretty consistent across the board. I can change it if I want to, and if you have another instructor, they might change it. But 0.05 is generally what you can expect. Even in real life, the significance level of 0.05 is pretty common. You might change it, especially if the situations deem it necessary. For instance, what percentage of people die when I take this drug due to side effects? Well, you're going to want to make sure that you don't want to reject a true null hypothesis there. You might set your significance level even lower. But what ends up happening, and this is pretty advanced math, but what will happen is that this starts to increase. I know some of you are into nursing, which what I want you to think of, this 2 and 4, these two types of errors, think of it as like a false positive or a false negative. In nursing, a false negative is a lot worse than a false positive, because you're letting someone go who's sick and without treatment. It's a lot better to treat a false positive than to fail to treat a false negative. And so that's kind of the corollary, I guess you can say, of these two things in real life outside of math. All right, let's see if there's any more. There's nothing really left in this section, so I'm going to stop the video now. This is all the vocabulary that's needed in this first section to get to the actual math. How do we actually test these claims? So to recap, because this is very, very, very important, we would like to conduct a test. And I started this with, when do we expect our friend is cheating? Well, we will test the hypothesis that the coin is fair, something like that. We make, let's see, we use sample evidence to test this claim. So a statement's made, we collect evidence from a sample, and then we analyze that sample to see if that claim that was originally made has some gusto, if we actually believe it. There are always going to be two hypotheses at play. The claimed hypothesis, your friend claims the coin's not weighted. That coin is fair. Or that I say 42% of people in my classes get B's. Or 14% of people smoke. Or that the average salary at this company is $50,000. There's some claim that's made. And then also the alternate. What do you believe? Well, I actually believe that it's less than 42% of people pass your class, Nick. I believe that it's more than 14% of people that smoke. Or I believe that the average salary at this company is different from the $50,000 you claimed. Then you can set up those hypotheses, showing them as math statements. The null is going to show that the claim, so that the claim is that the proportion was equal to 42% in this case. And then the alternate will be the same exact statement mathematically. It's just that the symbol changes in between. You believe evidence suggests it's less than 42% in this case. After some math happens in the middle, which we will go over in the next few sections, we come up with either we reject the claim or we cannot reject the claim. So I reject the idea that it's 42% of people that pass your class, or I can't reject the idea that 14% of people end up smoking. Since these are the only two conclusions we can make, there are 4 total possible outcomes. 2 of them are you made the right decision. You either rejected a null hypothesis that is false. Good, I was lying. It's not 42%, and you rejected it. Good job. Or you fail to reject a null hypothesis that is true. So I say it's 14% of people smoke, and your evidence suggests, okay, I can't reject that. And in reality, if we were able to sample everyone in the world, and it is equal to 14%, then you made the right conclusion. I did not lie, and you did not reject me. However, there are two possibilities that could happen. You end up rejecting a true statement, or you end up not rejecting a false statement. Those can happen, and so some things go on in a higher level. If you take, I believe I learned this part down here on how this stuff comes about in Math 331 at Towson. So you guys can go on and change your major to math to figure out this part, but basically for our purposes, that a significance level is set so that this error happens only 5% of the time. And then by doing that, there's a lot of calculus that goes on in the background that changes the probability of this, and that's actually called the power of the test, but we don't have to worry about that. But that overall is it. That is why we're getting into these next few sections. Someone makes a claim, we want to gather evidence either in support of that claim or against it to make a conclusion. And the next two sections will be, how do we actually do that? So that was a lot of vocabulary I threw at you. Hopefully it sticks, because I will be using a lot of these words in the next few sections.